Hi everyone, I'm Tianshi from Tsinghua. Glad to see everyone on the cloud. In this talk, I will be presenting the paper, Deep Reinforced Bitrate Ladders for Adaptive Video Streaming. Video streaming is the predominant internet application, making up almost 3/4 of all traffic. And most video streaming services employ adaptive video streaming to ensure high quality of experience, we call that QoE, and to achieve a high bit rate, lower buffering, as well as low smoothness. So in the adaptive video streaming system, on the server side, video streams are pre-trunked and pre-encoded at various bitrates or quality levels. And on the client side, users often apply adaptive bitrate algorithms to pick the proper bitrates for trunks and to ensure the quality of experience. We often call the server-side encoding settings as the bitrate ladder. Recent work consider the bitrate ladder construction process as a nonlinear optimization problem and analysis all the possible resolution and bitrate pairs independently and pick the best pair that is close to the convex hull as possible. However, such schemes often analyze all the possible resolution and bitrate pairs, which is short of transcoding efficiency. In this paper, we show that the bitrate ladder should be optimized by taking several factors from different perspectives into account, including video contents, network capacity, and storage cost on the cloud. We collect several videos with different contents and report the rate distortion we call RDQ with the video resolution of 240p and 180p. Video content usually has a great impact on encoded video quality. Thus, we argue that the one-fits-all strategy can hardly always achieve satisfactory performance for various video contents. More, we further investigate the relationship between the average bandwidth distribution and the default bitrate ladder setting proposed by Pensive. The CDF session throughput curve in figure shows that the current network environments seldom consider all the range of bitrate candidates. Thus, motivated by the previous bitrate ladder scheme, we take the current network traffic conditions into consideration. And finally, that table lists the bitrate ladder settings. Specifically, we compute the average storage consumed for each raw video trunk and use robust MPC to evaluate the performance of each bitrate ladder via VMAF over HSDPA, or called Norway networks. Surprisingly, we observe that the bitrate ladder with too many tracks fails to obtain higher video qualities. So reporting together, we find that constructing a good bitrate ladder should consider video content features, current network traffic capacities, and especially the average storage cost on demand. So it's quite challenging for conventional heuristics to effectively combine such metrics from various perspectives. To that end, we propose DeepLadder, a deep reinforcement learning bitrate ladder construction approach. The reason why we leverage deep reinforcement learning since its capacities to generalize from raw fresh data without relying on handcrafted engineering. DeepLadder's basic system workflow is mainly composed of the transcoding stage and the online stage. In the transcoding stage, we leverage a neural network-based decision model for constructing the proper bitrate ladders and used assigned settings to transcode the videos for each trunk. In online stage, the encoded trunks are deployed on the server and wait for fetching. The neural network continually obtains the video quality and storage at the transcoding stage, as well as periodically receives the network states, such as the current network distributions and trunks feedback at the online stage. So please note that the algorithm will terminate after generating 6 bit rates in this paper. At each step, the learner picks the proper profile for the video in the resolution orderly. We attempt to use a neural network to determine the proper action for each resolution autoregressively. We mainly divide DeepLadder's input into 4 parts as shown in the figure. That is, the video features, network capacity, past actions, and storage weights. For the reward function, we aim to maximize the bandwidth utilization and average quality, and in turn, minimizing the average storage overhead. In the evaluation part, we attempt to evaluate DeepLadder on both CBR encoded and VBR encoded videos. The key challenge is that the CBR and VBR are 2 different coding methods. For CBR, it controls the transcoding process by adjusting the bit rate, while the VBR controls the video quality. The first is the CBR results. Compared with existing methods over various networks and videos, DeepLadder CBR improves the average quality of almost the current 10% and enhances the bandwidth utilization by 3% to 11% and reduce the storage cost by almost 40% and up to 55%. Moreover, results on DeepLadder VBR encoded videos also illustrate the significant improvements in average quality and reduction in terms of the storage costs. For more information, please read our paper. For example, we also show that DeepLadder is practical and can be deployed in a transcoding framework. Testing results on both the CPU and GPU devices indicate that DeepLadder achieves the aforementioned performance with only extra cost and very low extra cost with only 3.4 on extra costs compared with the original system, while saving almost 70% of overall overhead in comparison of the state-of-the-art heuristics. Here's the key takeaway here. We investigate 3 critical features for constructing a good bitrate ladder. Moreover, we propose DeepLadder, which is the first deep reinforcement learning-based approach to solve the problem. We train the DeepLadder over various videos, dataset, and network traces. As expected, DeepLadder demonstrates the superiority of the algorithm compared with prior approaches. We have published the datasets in the THO Media and DeepLadder. Thanks to everyone.